Hello, dear viewer. In this video, I want to demonstrate two techniques for rendering Mandelbrot fractals. In order to demonstrate the techniques, we will use this 1-minute-long zoom that is playing right now. Currently, every frame in the zoom video is rendered raw. That means the escape time. So the number of iterations it takes to determine if a given pixel is in the Mandelbrot set or not is determined for each pixel. In this video, we will go over two techniques that let us skip the escape time determination of many pixels per frame. But for now, let's just finish watching this zoom. Before we are getting into the techniques, I want to talk about a key property of the Mandelbrot set, which we will take advantage of in our techniques. In order to define the property, I have prepared a little visualization. Let's split the screen into a left part and a right part and treat them separately. Let's first focus on the left part. This black blob is our set of interest. Let's take any 2 points, A and B, in this set. We see that we can draw an orange path from A to B without ever leaving the set. Visually, it is clear to us that we could have drawn such a path no matter where we placed A and B. It is for that reason that we call the set connected. Now let's draw another path in green from A to B. Now let's imagine turning the orange path gradually into the green path by ever so slightly adjusting each point along the orange path towards the green path. Now we have to ask ourselves, can we turn the orange path into the green one with that process in such a way that at no point in time any part of the path is outside the set? The answer is yes. Visually, we again see that we could have done that for any 2 paths from A to B and for any 2 point A and B. It is for that reason that we call the set simply connected. Just for testing our understanding, let's look at another set at the right side of the screen. Let's again pick 2 random points A and B in the set. We again see that we can connect them with a path inside the set, so the set is connected. Let's now draw a second path from A to B. Now we again try to turn the orange path into the green path gradually. But now we realize that we can't do that without having part of the path being outside the set in an intermediate step. For that reason, this set is not simply connected. It is clear to us that simply connectedness implies connectedness. Now 2 questions to you. Take a guess. Is the Mandelbrot set connected? Is it simply connected? It turns out the Mandelbrot set is connected, and in fact, it is even simply connected. In order to justify the upcoming techniques, we go even a step further and assume that every approximation of the Mandelbrot set, which we arrive at when we iterate the Mandelbrot formula only a finite amount of times, is also simply connected. Now let's have a look at our first technique. Let's call it the rectangle processing algorithm. This is the first frame of the zoom video, but this time it is rendered with the rectangle processing algorithm, and on top of that, the relevant rectangles are highlighted in white. Let's get something out of the way right off the bat. Since I am rendering with 12 threads, the image you see is divided into 12 horizontal slices, each thread rendering a different slice. That is not mandatory for the rectangle processing algorithm, but that is the way the image is rendered, and so that is the reason why you can make out these 12 horizontal slices in the image. Within each slice, the rectangle processing algorithm is applied to the whole slice. The algorithm works in the following way. Evaluate all escape times of pixels along the boundary of a rectangle. If all escape times are the same, then assign this escape time to all pixels within the rectangle. If not all escape times are the same, then subdivide the rectangle into smaller rectangles and repeat the process for each of those rectangles. Lastly, if a rectangle turns out to be already very small, then evaluate the escape times of all pixels within that rectangle in a raw manner. We justify the assignment of inner pixels with the escape value of the border of a rectangle with the fact that the Mandelbrot set is simply connected, and our assumption that this is also the case for aforementioned finitely iterated approximations of that set. The idea is that our set cannot have any holes, like the not simply connected counterexample that was at the right of the screen earlier had, and therefore we can assign the interior of a rectangle with constant escape time along its border with the same escape time. So in the image, we skip the escape time evaluation for every pixel which is inside a white rectangle. Pixels, which are not inside any rectangles, were evaluated raw due to rectangles containing them becoming too small. I am splitting the screen into a top half and a bottom half now. In both halves, the zoom video with rectangle processing algorithm will play. In the top, it will play with the rectangles highlighted, and in the bottom half, it will play without highlighting. Now let's have a look at our second technique. Let's call it Escape Area Processing Algorithm. This is again the first frame of the zoom video, but this time it was rendered with the Escape Area Processing Algorithm, and the boundaries of the various escape time areas are highlighted white. Of course, the image is still partitioned into 12 horizontal slices due to multi-threading. The escape area processing algorithm works in a similar manner as the rectangle processing algorithm, but it is more sophisticated. Instead of guessing rectangles and hoping that escape time along the border is constant, we start at a border, that is, a pixel which is either a border pixel of the slice, the top left corner for example, or a pixel that has a different escape time than one of its neighboring pixels, and from there, we trace the escape time border of its escape time. This tracing can easily be implemented with a wall-hugging maze-solving algorithm, where different escape times are walls. Once the maze-solving algorithm arrives at the starting position and facing the same direction, a full border to an escape time area is traced out. Once all borders are evaluated, their interiors can be filled in one swoop over the image. Unlike with the rectangle processing algorithm, the escape area processing algorithm has not an as clear-cut condition for when to start evaluating pixels raw, since we only know how large an escape time area is after we have traced its border. For that reason, you will see way more white pixels than with the rectangle processing algorithm, since no pixels were evaluated the raw way, even in tight spots. Generally, with the escape area processing algorithm, you can skip more escape time evaluations than with the rectangle processing algorithm. I am now splitting the screen in the same manner into a top half and a bottom half as before, and let the zoom videos play. Lastly, I want to talk about artifacts. When we render by using the rectangle processing algorithm or the escape area processing algorithm, then there can occur some discrepancies compared to a raw render. For that, let us look at this frame of the zoom video, and here let us zoom into the location indicated by the red circle. This is the zoomed-in version in the raw render. Let's put this version in the top left corner of the screen, and let's put the zoomed-in version of the rectangle processing algorithm in the top right corner. Now we can clearly see a discrepancy highlighted by the pink circle. To see why this green pixel is black in the rectangle processing algorithm, let us put the same zoomed-in version of the rectangle processing algorithm, but with highlighted rectangles in the bottom right corner. Now we can see that that pixel was enclosed by a rectangle whose border escape time was black. That poor little green fella got swallowed. The orange pixels just above the green one were lucky that around them the rectangles must have gotten too small, and the raw render kicked in. Since the escape area processing algorithm is even more potent than the rectangle processing algorithm, such swallows happen in the escape area processing algorithm, even easier. To illustrate that, let's put the zoomed-in version of the escape area processing algorithm in the bottom left corner. Here we see that not only the green pixel got swallowed, but also 4 additional pixels, 2 orange ones and 2 blue ones, highlighted in the red ellipse. These artifacts occur because, as we can clearly see, the black area is not simply connected. You might be wondering why that is the case. It is due to pixelation of the Mandelbrot set, that is, the evaluation of escape times at discretely distanced pixel coordinates. Let me illustrate that. Let's say this black blob is our Mandelbrot set. It is clearly simply connected. In order to turn this set into an image, we have to decide pixel by pixel if the pixel should be depicted as in the set or not. So let us put a pixel grid on top of that set. Now let's color every pixel with the color in its center. And now we see that the depiction of the set is suddenly not simply connected anymore, even though the set itself was. We can see the culprit highlighted in the red ellipse. The 2 black pixels neighboring each other in that ellipse make it seem like they are connected within that ellipse. But in reality, the parts of the set they should represent are not connected within the ellipse. The information that there is a gap in the set got swallowed upon pixelation of the set, and this ultimately leads to swallows when rendering with the rectangle processing algorithm or the escape area processing algorithm. Thank you very much for watching. If you liked the video, please leave a like and consider subscribing. It really helps the channel out. Please let me know in the comments if there are any topics or videos you want to see next.